Hello everyone. Um, Today we are going to see about the concept of a Bellman's Ford algorithm and myself, Mrs. G. Marishwari, working as an assistant professor in the Department of Information Technology, Ramco Institute of Technology. So this is the overview of this presentation. First, we are going to see about what is meant by shortest path problem and what are the issues in a shortest path problem. How can we overcome that with the help of the Digitro's algorithm? In Digitro's algorithm also there are certain issues, so that we are moving towards Bellman Ford algorithm. So we are going to see about the step-by-step procedure of procedures of Bellman Ford algorithm, then advantage, disadvantage, and certain applications of Bellman Ford algorithm. So first, what is meant by shortest path problem? In a graph theory, the shortest path problem is the problem of finding a path between two vertices in a graph. The objective here is to minimize the sum of weights of the consequent edges that is present in between two individual vertices or nodes. So we may often consider the problem of finding shortest path between two intersections on a road map as a shortest path problem. So one of the solution we can able to find the solution for the shortest path problem using the Digitras algorithm. So the Digitras algorithm is mainly used to find the shortest path from the given source vertex to all the other vertex in a given graph. But the Digitras algorithm is consist of certain issues. Even though it solves the shortest path problem, it has certain issues. The issue here is it will not work properly, or it will not properly work for the graph consists of negative edges. Digital's algorithm is suitable only for the graph with positive edges. If the graph consists of any negative edges, it may or may not give the proper result. So that is one of the issues present in the Digital's algorithm. So that we are moving towards the Bellman Ford algorithm. The Bellman Ford algorithm help us to find the shortest here also. Yeah, find the shortest path from the given source vertex to all the other vertex of a given weighted graph. Here the working procedure is somewhat similar to the Dijitra's algorithm, but it can also work well for the graph which consists of the negative edges. For example, consider the below diagram. Here there are two nodes are available. In between the two nodes, there is a where edge is present. The edges consist of the negative weighted edge. So this is an example for the graph which consists of the negative edge. So this is the step-by-step procedure for solving the shortest path problem using this Bellman Ford algorithm. So the first step here is to prepare the list of edges present in the given graph. Then the second step is to relax all the edges. For here we are need to relax the edges for n minus 1 time. Here n represents the number of vertices. So we are needed to relax the given edges up to v minus 1 or n minus 1 times. This is the pseudocode for the Bellman Ford algorithm. Here we are concentrating on only two steps. One is the initialization step and another one is the relaxation step. In initialization step, the first node, that is the source node distance is initialized to the value of 0. The distance of the source node is initialized as 0. And for all the other vertex in the given graph, we need to assign the distance value as infinity. So in the initialization step, we need to assign the distance of source node as 0 and the distance of all other vertex as infinity. So next step is relaxation. In relaxation step, we need to relax all the edges for n minus 1 or v minus 1 times, where n or v is the number of vertices. Here we should check whether that particular edge is present in the that here u comma v represents the u is the starting vertex, v is the destination vertex. If the edge that is present between u and v belongs to the list of edges that is present in the graph, if it is so, we should calculate this. First, we should find the distance of the destination vertex is greater than the sum of the distance of the source vertex and the weighted cost of the edge that is present between the source and the destination. If the destination distance is greater than the sum of these two, then we should update the some value as the value of the distance of that particular destination vertex. If the destination vertex in initial stage, defaultly the destination distance of the destination vertex is infinity. So it is defaultly greater than this some value. So at the starting state, we must update this sum value to the distance of the destination vertex. We should do this repeatedly until v minus 1 times. Consider this example graph. So here there are nearly 4 plus 3, 7 vertex are present and totally 10 edges are available. So first step of this Bellman Ford algorithm is to list out all the edges present in the given graph. Here I have listed out the list of edges that is present in the given graph. First edge is present in between node 1 and 2. So it is represented as 1, comma 2. Second vertex is 1 between 1, 3. Then third edge is between 1, 4. Then between 2, 5. Then between 3, 5. Between 3, 2. Like this. Totally 10 edges are presented in the given graph, which is listed here. Now the next step is we need to relax all the edges. We need to relax the edges up to n minus 1 time or v minus 1 time, where v is the number of vertex, right? Here there are totally 7 vertex are present. So we need to relax up to 6 times. 7 minus 1, 6 times we need to relax the edges. So initially we mark the distance of all the vertices. In the vertex, near to the vertex, we need to mention the distance value. So near the source vertex 1, here I have updated the distance of the source vertex as 0. And near the vertex 2, I have updated the distance of this vertex as infinity. Apart from the source vertex, all the other vertex distances initialized as infinity as it's shown in the given graph. First, we are going to relax the edge that is present in between the vertex 1 and 2. So, the weight of the edges that is present between 1 and 2 is 6. So, we should calculate the distance, right? So, distance of the destination vertex 2 is infinity. Initial distance of the destination vertex 2 is infinity. So, distance of the source vertex is 0. So, d of u is 0 here. Here, d of v is 6. D of v is infinity. D of u is 0 and C of u comma v, that is the weighted edge between 1 and 2 is 6. Then 0 plus 6 is equal to 6, which is greater than which is less than infinity, right? So therefore we should update the distance of this particular node 2 as 6. By cancelling this infinity, we should update it as 6. Similarly, we next consider the next consecutive edges. So consider the distance between the vertex 1 and 3. Its weight is 5. Initially, the distance of this vertex 3 is infinity. So here it is mentioned here, d of v is infinity. We should also represent these two values. Distance of the source vertex is 0 here, and the cost of edge between u and v is 5 here. Then 0 plus 5, which is equal to 5. 5 is less than infinity, so the constraint is true. If the constraint is true, we should update the distance of vertex v as v with the sum of these values. So d of v is now replaced by 5 instead of infinity. We cancel the infinity here and replace the value 5 instead 5 here. Similarly, for this particular node, we cancel the infinity and replace the value 5 here. It is shown in this next figure. So see here, initially the value of our distance value of this particular node is mentioned as infinity. Now it is updated to 6. Distance value of this node 3 is initially represented as infinity. Now it is updated to 5. Similarly, the distance value of this particular node is initially mentioned as infinity. Now it is updated to 5. Next, we are going to take the edges to edge that is present in between the vertex 2 comma 5. Here the weight of the edge is -1. So again we need to calculate this. Here the destination vertex is 5 and its initial value distance value is infinity. So it is mentioned here, and the source value distance is mentioned as a source vertex distance is mentioned as 6. It is represented here. The weight of the edge is mentioned here. So 6 plus 1, that is 6 minus 1 is 5. 5 is less than infinity. So the value of 5 is updated to as the distance value of this particular node. So at the next step, this particular infinity is updated to be the value of 5. Next, we take the edge 3 comma 2, uh, edge that is present in between the vertex 3 comma 2. So in between this vertex 3 comma 2, the edge that is present is -2. So here the destination vertex is uh, node 2, and its distance already its distance value is 6. It is mentioned here. So the distance of the source vertex is 5. It is mentioned here. So the cost of the edge that is present between 3 to 2 is -2. That is represented here. So 5 plus 2 5 plus -2 is the value become 3, where 3 is less than 6. So here the value of the sum is less than the distance of the destination. So the distance of destination is updated with the sum value. So d of 2 become 3. So it is clearly mentioned in this graph. So instead of infinity, we update the value 5, and here instead of 6, we have updated the value 3 here, distance value 3 here. Next, we are going to take the edge 3 comma 5 that is present between the vertex 3 comma 5. So the edge that cost between 3 comma 5 is 1. Here the destination vertex is 5. Its distance value is 5. So which is mentioned here. And the source value, source node is 3 and its distance value is also 5, which is also mentioned here. So here the edge cost is 1. So 5 plus 1 becomes 6, where 6 is greater than 5. So there is no need to modify the distance of the destination vertex, because the distance of the destination vertex here is smaller than the sum value. So there is no need to update the distance here. Next, we are going to take 4 comma 3. So the edge that is present between the vertex 4 comma 3. Here the edge uh, weight of the edge value is -2. So here the source vertex is 4 and the destination vertex is 3. The distance of the destination vertex 3 is 5. So which is mentioned here. The distance of the source vertex 4 is 5, which is also mentioned here. So the edge cost is -2, that is mentioned here. So 5 plus -2 is become 3, where 3 is less than the distance of the destination vertex 5. So 3 is updated as the distance of the destination vertex. So d of 3 is now updated to 3. So this will be represented in the next graph. So d of 3 is updated to the value 3. So next we are going to take the edges that is present between 4 comma 6. Here 4 and the 6 is here. We are going to take this particular edge. Here the destination vertex is 6. The distance of the destination vertex is infinity, which is mentioned here. And the distance of the source vertex is 5, which is mentioned here. The cost of edge that is present between 4 comma 6 is -1, that is mentioned here. So 5 minus 1, the total value is 4, which is less than infinity. So the distance of the destination vertex is updated by the lowest cost value, that is 4. So d of 6 become 4. So infinity is updated to 4. Next, we take the value. We take the edge that is present in between 5 comma 7, vertex 5 comma 7. So here is the vertex 5 and here is the vertex 7. So the edge that is present in between 5 comma 7 cost value 3. Here the destination vertex is 7 and its distance value is initially mentioned as infinity. So here it is represented as infinity. The distance of the source vertex is mentioned as 5. Here it is represented. So the weight of the edge is 3. That is represented here. So 5 plus 3 is equal to 8. Surely 8 is less than infinity. So the distance of the destination vertex 7 is replaced by 8 instead of infinity. So instead of infinity, we replace the distance of the node 7 as 8. It will be shown in the next diagram. Next, we are going to take the vertex that is present in edges that is present in between the vertex 6 and 7. So here 6 is the source vertex and 7 is the destination vertex. The destination vertex d of 7 values already updated as 8, that is represented here. And source vertex distance is already updated to 4, that is represented here. So the distance between this particular source and destination is 3, that is represented here. So 4 plus 3, the value is 7, which is less than the value 8. So d of 7 is already updated as 8. Now it is again updated to 7. Initially it was 8, initially it was infinity. When considering this particular edge 5 to 7, it was updated to 8. Now again it was updated to 7 by considering this particular edge 6 to 7. The updations are shown in the given graph. So the node 5 is distance of the node 5 is replaced by 5. Distance of node 7 is replaced by 7, and the distance of node 6 is replaced by 4. Here we have relaxed all the edges for one time now. We need to do it again and again for 5 more times, because we need to relax the edges up to n minus 1 or v minus 1 time. Here there are totally 7 vertex are there. So we need to update the vertex up to 6. We need to relax the vertex up to 6 times, edges up to 6 times. Here this table shows the values of distance values of each and every node after every relaxation step. So initially there is no relaxation of edges is present. So at the initial stage, the distance of the source vertex 1 is 0, and the distance of all the other vertex is represented as infinity. After one step relaxation, the distance of source vertex 1 is again 0, and the distance of all other vertex is updated. So this is the updation done after a single relaxation. Similar to this, we needed to relax the edges up to n minus 1 time. Here we needed to relax up to 6 times because there are 7 vertex are present. So this diagram, this is the last step. Here we just stop the relaxation. So in this table, here the distance value is not changed after 3 times. So after the third step, there is no changes in the distance here. So this diagram shows this is the final graph that we drawn after relaxing the edges up to 6 times. So here the source vertex is the distance of source vertex is 0. Distance of the vertex 2 is mentioned as 1. Distance of vertex 3 is 3. And the distance of vertex 4 is 5. Distance of vertex 5 is 0. Distance of vertex 6 is 4. And then finally distance of vertex 7 is 3. Here it is shown here. So this is the final solution of the given graph. So time complexity of the Bellman Ford algorithm is depends on the number of vertex and the number of edges. Here we need to relax all the edges. So we need to consider edges here. And we are relaxing the edges up to v minus 1 time. So we are also needed to consider the vertex here. So the time complexity is order of v into e. Suppose the number of vertex is n and the number of edges is also n, then the time complexity become order of n square. The advantage of Bellman Ford algorithm is here we can able to handle the negative graph with the negative edge. Uh, um, Many prior algorithm doesn't able to handle the graphs with the negative edge, but a Bellman Ford algorithm can able to handle this type of graphs, and it can also able to detect the graph with the negative cycles. limitation of the Bellman Ford algorithm is here we can't able to find the graph with a negative cycle, but we can't able to find the solution for the graph which consists of the negative cycle. Negative cycle is nothing but it is a directed cycle graph whose total weight is negative. For example, consider this graph. Here its total weight become negative, where total weight are adding the sum of the edges. 3 plus 5, 8, 8 minus 10, which is equal to minus 2. If your graph is consist of a negative cycle in the sense, then there is no meaning for the shortest path to find here. So it is not able to, so the Bellman Ford algorithm is not able to find the shortest path for the graph with the negative cycle. This is the limitation. And the main application of the Bellman Ford algorithm is the Google Map, which is mainly used to find the shortest path between the two particular location. Here we can consider the map as a graph, and the location in the map are considered as the vertices, and the roads are considered at the edges, and the length of the roads are considered as the weights that is present in between the vertices. So these are about the Bellman Ford algorithms. I hope the video will be useful for all, and thank you.